Welcome to The Explainer. Today we are diving deep into something we use every single second, but maybe don't totally understand: computer networks. We're going to look at how they're built, how they talk to each other, and maybe the most fun part, how attackers try to break them.
I mean, really think about it for a second. You click a link, and boom, a website from a server halfway across the globe just appears on your screen. It honestly feels like magic, right? Well, it's not magic, but it is an absolutely brilliant system of hardware and rules working together. Let's pull back the curtain and see how it all works.
So, at the most basic level, a network is just a bunch of devices that are connected. That's it. It could be the laptop, phone, and smart TV in your house, all the computers in a giant office building, or, the billions of devices that make up the entire internet. The whole point is to share stuff. Okay, so to really get this, let's start at the beginning. We're going to talk about the actual physical stuff, the hardware, the nuts and bolts that make all of this digital communication even possible.
First up is a little box you definitely have sitting somewhere in your home: the router. The best way to think about a router is as the internet's traffic cop. Its entire job is to direct the flow of data. It makes sure that your request to watch a goofy cat video actually gets to the right server, and then, crucially, that the cat video finds its way back to your phone and not your neighbor's.
So how does this little traffic cop do its job? Well, when you want to send something out to the internet, your router takes that data and chops it up into tiny little pieces called packets. For every single one of those packets, it makes a super fast routing decision, kind of like checking a map to find the best route. Then it forwards the packet on its way. It also uses this really slick trick called Network Address Translation, or NAT, which helps manage all the different devices in your house. We'll touch on that again in a bit. It's pretty cool. Now here is something that trips a lot of people up: the difference between a modem and a router. Think of it like this. The modem is the on-ramp to the big internet highway. It's what connects your house to your internet service provider. But the router? The router is what creates your own private little network, your local area network, or LAN. It takes that one big internet connection from the modem and shares it with all of your devices. So if the router is the main traffic cop for the internet highway, then a switch is like a local post office. It operates inside a local network, like in an office building. Its job is to manage the flow of mail, or data, just between the devices that are right there in the same building. And this is where switches get really, really clever. Every device that can connect to a network, your computer, your phone, everything, has a unique serial number burned right into its hardware. It's called a MAC address. So when PC1 wants to send a file to PC4, it tells the switch. The switch looks at the MAC address and sends that data directly to PC4, and only PC4. Nobody else on the network even sees it. It's like a private, sealed letter instead of a postcard for everyone to read. This intelligence is what makes a switch so much better than an older, dumber device called a hub. A hub is, well, it's not smart. When a hub gets data, it just yells it out to every single device connected to it. A hub is like shouting a secret across a crowded room and just hoping the right person hears it. A switch, on the other hand, is like walking over and whispering it directly into their ear. It's way more efficient and a whole lot more secure. Okay, so we've got the hardware pieces, but how are they all physically plugged into each other? The blueprint for how a network is laid out is what we call its topology. Let's look at one of the classics. One of the simplest and oldest designs out there is the bus topology. Just picture a single, long street. All the houses on that street, or in our case, all the computers and printers, are connected directly to that one road. That main road is our central cable, the bus, and all communication has to travel up and down that one shared line. Now the benefits are pretty obvious, right? It's super easy to set up, it's cheap because you don't need a lot of cable, and for a really small network, maybe for a quick LAN party back in the day, it gets the job done. But, and this is a big but, the downsides are huge. The absolute killer is that single point of failure. If that main bus cable breaks anywhere, the whole network is dead, kaput. It's also tough to add new devices without slowing things down for everyone. It's a simple design for sure, but this is exactly why modern networks use much smarter, more robust layouts like star or mesh topologies to make sure one little break can't take down the whole show.
Okay, we've covered the physical hardware and the blueprints for connecting them. But how does a piece of data actually know where to go? This is where we get into the logical side of things, the rules of the road, like addresses and protocols.
And here is the absolute key to everything. To send or receive anything on a network, every single device needs an address.
That's its IP address. It works exactly like the mailing address for your house. It gives the network a unique destination to send information to. Without an IP address, data packets would just be lost, wandering around the internet forever with no place to go.
Hey, remember NAT, that clever trick I mentioned routers use? Here's how it works. Your router creates a private little neighborhood network for your home and gives every device, your laptop, your phone, your TV, its own private internal IP address. But when any of them want to talk to the big public internet, NAT cleverly translates all of those private addresses to use the one single public IP address your internet provider gave you. It was an amazing solution to the problem of running out of IP addresses. And, as a bonus, it adds a nice little security barrier.
But that one layer of security isn't going to be enough, not even close. So let's pause. We've designed our network. Our hardware is all connected, our addresses are working, data is flowing, everything is great. Now, it's time to shift our thinking completely. How would we break it? See, to properly defend a network, you have to learn how to think like an attacker. You have to think offensively. This next part is all about putting on that hacker hat and understanding the strategies and tools they use to find weaknesses and get in. A huge part of this offensive security world is something called penetration testing, or pen testing for short. This is basically ethical hacking. A company will literally pay a security expert to launch a controlled fake attack against their own systems. The goal isn't to do damage, the goal is to find all the holes before a real attacker does so they can get them patched up. And it's not just random chaos. A real pen test is a structured process. It starts with reconnaissance, gathering intelligence on the target, like a spy. Then you move into scanning, using tools to probe the network for known weak spots. After that comes the fun part, exploitation, where the tester actually tries to break through the defenses. But really, the most critical step is the last one, the report. That's where they give the company a detailed map of everything that's broken and exactly how to fix it. So during a test, these ethical hackers are using a whole bag of tricks. Things like phishing, which are those sneaky emails trying to trick you into giving up your password. They'll try password cracking to just guess their way in. They might try a man-in-the-middle attack where they secretly listen in on your connection. And then there are more technical attacks like SQL injection or cross-site scripting, which try to trick a website into running malicious code. These are the real threats they're looking for.
But finding problems after everything is already built is one thing. What if you could do it even earlier? That's the idea behind threat modeling. This is a proactive strategy. Before you even write a single line of code, before you plug in a single cable, your team gets together and thinks like a hacker. You ask, okay, what are we building? What could possibly go wrong? And what are we going to do to stop it? It's all about building security in from the very start.
So when you boil it all down, it comes to this. Your network is basically your digital home. And just like a real house, it has doors and windows that an intruder could try to get through. Understanding how it's all put together is step one. But the real security question, the one you have to keep asking yourself over and over is, are you sure all of those doors and windows are actually locked?